at the origin, okay? If we don't want it at the origin, how do we get it someplace else in our CAD system other than magically dotting a button and then spinning a sphere up there?
As in like x minus x naught quantity squared plus y minus y naught quantity squared.
Exactly. So just by doing an offset, so x minus x naught, where x naught is the x location of the sphere, squared, quantity squared, plus y minus y naught, quantity squared, y naught being the y location of it. So we can represent a more general form, and that's whenever we're doing this type of object in a CAD system, we're basically building what is called a CSG, a constructive solid geometry. It's a primitive, and the earliest CAD systems were built on primitive mathematical forms, and they used that to represent a sphere at any location, okay? So that was the exact mathematical form that they stuck in. Where do these things show up? Well, they show up all over the place, okay? One example is a water tower. Is there a more general form than that equation? Well, yeah, we could go with an ellipsoid, okay? How is an ellipsoid defined? Well, it's x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. Are those shapes found? Well, just last summer, I was in Dubai and Abu Dhabi, and they had some crazy buildings that I stared at while I was over there. And it's amazing that some of those buildings are very ellipsoid in shape. Now, not a perfect ellipsoid. They just took one side, another side, and they moved them closer together, as in the first example, it's in Abu Dhabi. And in the second example, again, they kind of took the left half of it and kind of made an elliptical shape. This is a BMW 3 Series, and if you look carefully at kind of the nose of that, that nose is very ellipsoidal in shape, okay? So we still see some of these second order shapes and geometry appearing. A cylinder has a mathematical definition. It's pretty simple. X squared plus y squared equals a squared. Those things show up all over the place as cylinders, as shafts in cars, and things like that. If we wanted to orient them not along the x-axis, what would the equation be? Well, if we wanted it along the x-axis, not the z, it would just be y squared plus z squared equals a squared. How do we represent the ends? Are the ends represented in that mathematical equation? Now, it's an infinite cylinder, so in the CAD system, when we're building cylinders as primitives, we have to have three equations. We have to have the equation of the cylinder. We have to have an equation that represents the capping of both ends. And so in this simple example, we would say z equals minus 1 for one end and z equals 10 for the other end. How do we do that in the CAD system? Well, we define it starting on a plane and moving away from the plane some distance. We already talked about that. Okay. What is the equation of elliptical cylinder? What is the equation of a parabolic cylinder? So all of these are very traditional forms that have been used and are still being used in industry. For example, this parabolic cylinder is typically the equation that's used for the leading edge of a wing. Okay? They have not moved away from that since the Wright brothers started putting leading edges. Okay? I don't know that the Wright brothers actually mathematically did it, but shortly after that, when they started really looking at airflow over a wing, they moved to this parabolic cylinder equation. hyperboloid of one sheet and how it's defined has one minus sign. Where do we see those shapes? Cooling towers, right? Why do we see those shapes as cooling towers? Are they better than just a cylindrical cooling tower? And if so, why? They're more stable, okay? Those things are very tall. They have a lot of wind shear in some places. A cylinder in and of itself does not have a stable base. These things have a very stable base, okay? And they provide some better cooling just because of the shape of them. A hyperboloid of two sheets has an equation where it's two minus signs. So it's basically the same equation. It's just you flip the minus signs on the other two terms. Quadratic cone. Notice that we're going through these fairly quickly because we want to get to the general surface definitions that are in CAD systems. So this quadratic cone that's out there, is it used in industry? Well, this nose, called the radome of the F-16, is very conic in its shape, okay? Provides a very good airflow over the rest of the plane. Elliptic paraboloids and its definition. That shape right there is basically the intake or inlet for the engine. Notice that you can't see it very well, but the top side is another elliptic paraboloid. So they've got kind of half on the bottom, and then they've reused that same shape under the belly of the plane. Famous saddle shape. Where does that appear? Okay. It appears on the wing-to-body fairing of every airplane. Okay. Every airplane has a wing-to-body fairing on it, and so you can look at, if we look at the actual representation of the surface, we can see that the wing would actually be kind of coming out of this portion of the saddle, and we would have to change the, part you straddle to be the fuselage of the airplane itself. When I graduated with my bachelor's degree from BYU, the very first job, or one of the first jobs that I did at Boeing, was to work on the design of the wing-to-body fairing for the 757. Okay. So it was in the early days of CAD. CAD was a great drafting tool when I graduated. It was just barely becoming a surface modeling 3D CAD system. And one of the very first projects done for Boeing on a CAD system was to lay out the wing-to-body fairing for the 757. They gave us hundreds of what were called master dimensions. They were just XYZ coordinates. The XYZ coordinates defined, in essence, curves that were taken that basically represented where the wing went into the fairing and where the fairing attached to the body of the airplane. We had all of these points, and we had to basically fit a saddle shape through those points and correct them when they weren't in the right location. So, okay, on to what is referred to as a Bezier surface. This presentation has been uploaded to TCC, so I would encourage that you kind of open it up and look at it. It's a little bit of an eye chart to try and see what these blending functions